Dear colleagues, let me present to your attention the result of the research named Theoretical and Experimental Investigation of Error Detection and Error Correcting Ability of Rank Codes. Speaker is Tetiana Gryshchuka. The idea of using rank relationships of the distances between system states in parametric space to identify the states of control system was expressed by the authors back in 1995 at a scientific technical conference which was called then Control and Management in Technical Systems. This idea was extended in the direction of developing a theory on the application of ranked relations for the unified representation and processing of information about the states of systems described in different parametric spaces: deterministic, probabilistic, logical, fuzzy, approximate, and other. The concept of rank configuration and rank potential codes for their coding was introduced. Potential codes were named by analogy with electric field, where the voltage between the points of the field is determined by the potential of the charge located at these points. In parallel with theoretical studies, work was carried out on the practical application of rank codes in decision-making systems. Patents were also obtained for the methods of pattern recognition and information transmission using potential codes. The research conducted and presented in this work is relevant today. For example, the use of difference-preserving codes for decision-making, proposed by foreign authors, is able to cover the entire set of rank configurations between states of control systems. This limits the possibility of their use for decision-making in management systems. Research conducted in modern foreign works on the construction of optimal maximum rank distance codes is dedicated to improving the reliability of information transmission in computer networks, and not in the direction of using codes for the unification of information description and decision-making. To complete the research carried out by the authors, the works on the theoretical assessment of the corrective ability of the proposed rank codes remain relevant. The topic of the work that we present at this conference belongs to the direction of research on interference resistance and the corrective ability of rank codes when they are used for the transmission of rank information and the communication channels of the control systems. The results of this research carried out in the previous works of the authors showed that unlike the well-known standard in which it is only possible to detect the presence of errors, but there is no possibility to localize and correct them, the proposed rank codes allow to detect, localize, and correct all asymmetric errors and, to a lesser extent, symmetric single errors. Since this result was obtained on a rank configuration of size m equal 4, the problem arose of estimating the theoretical limit of the localizing and correcting ability of rank codes for rank configurations of different dimensions. Let's formulate a problem. The rank code is a set in the form of m binary words, the appearance of which depends on the rank configuration of one of the k admissible states of the control system. This code, by its nature, is a code with a constant weight. it is necessary to carry out a generalized theoretical assessment of the localization and error-correcting ability of rank codes at the output of the information transmission channel of the automated control system. The following theorem was provided by the authors. For rank configuration of dimension m, the Hamming distance d between rank code words is equal to quotient 2. The identification of the theoretical model was performed experimentally on the examples of specific rank configurations of dimensions m equal 4 and m equal 5 using models of rank configurations in the form of incidence matrices, the rows of which form the DRP codes of the vertices of the rank simplex shown in figure 1. On this slide, evaluation of error detection and error correction for rank configuration of dimension m equal 5 is presented. Experimental investigation of error correcting ability of DRP codes. In the table 1, an additional 1 is entered in the code of word C in the 5th digit. This is an asymmetric error. This code word is localized as erroneous by the number of units p equal 4 that more than 3, and since there are more than 2 units in the 5th column of the matrix, the localization and the correction algorithm should fix it. In the table 2, in the 6th digit of the code of word A, value 1 is replaced by 0. This code word is localized as false by the number of units p less than 3, and since there are less than 2 units in the 6th column of the matrix, the correction algorithm must write a unit in the 6th digit. The number of different variants of symmetrical errors can be determined by the formula 3. Analysis of symmetrical errors in addition to the erroneous code words also requires to analyze the verification matrix G of the rank distances between all pairs of code words. The distance between two code words is calculated according to the expression 4. Examples of the correct DRP code and its verification matrix G are shown in figure 3, and the wrong DRP code and its verification matrix G are shown on figure 4. Verbal description of the error correction algorithm in the run code. In the first step, a two-dimensional array of m by n size of m code words received from channel is formed in the decoder memory, where n is the bit rate of the code. Under the condition of error-free transmission, this array will correspond to the incidence matrix of the transmitted rank configuration of the system states, and each row of the matrix will correspond to the correct DRP code word. In the second step, by counting units in each line of the matrix, code words with asymmetric errors are localized in the case of t not equal to m-1, where t is the number of unit points in the word. Correction of asymmetric errors is carried out according to the procedure. If the number of units t greater than m in some words, then columns of the array of code words are scanned, and in the found erroneous words, units are replaced with zeros point in those digits whose columns contain more than 2 units point. If the number of units point in some word is t less than m-1, then the columns of the array of code words are scanned, and in the found erroneous word, zeros point are replaced by units point in those bits whose columns contain less than 2 unit points. In the third step, the columns of the array are scanned and the presence of symmetric even errors is detected in the case of columns with units points in which the number of units is not equal to. Localization of the erroneous code word is carried out by using the verification matrix G according to the following procedure. Those rows of the matrix that contain 2 units point are marked. If there is more than one such code word, then the one whose index is contained in the indices of pairs of indices twice is chosen by false. In the fourth step, the numbers of damaged bits are located and corrected. For asymmetric errors, they are determined by the presence or absence of the necessary unit points in the words. And for symmetric errors, as a rule, the column with zeros in the verification matrix of the code word distances obtained by the logical operation AND over all pairs of code words show a bit with a replacement of 1 to 0. And the column with 3 unit point is a bit with 0 to 1 replacement. To implement the algorithm, a Python program was developed, which is commercial product and can be provided upon separate request. To check the adequacy of the developed algorithm on the ability to detect and correct errors in rank codes, software testing was conducted, part of the results of which are presented below. The results show that the developed algorithm correctly localizes and corrects both asymmetric and symmetric errors in the code. The theoretical and experimental studies carried out in the work showed that these codes are highly resistant to communication channel interference and make it possible to localize asymmetric and symmetric errors in them with the help of simple algorithms. The work theoretically proved that the Hamming distance d between the code words of the DRP-code is equal to 2 by m-1 - 2, which provides the possibility of localizing errors with a multiplicity of 2 by m-1 - 3 and correcting errors with a multiplicity 2 by m-1 - 3 divided by 2. The corrective ability of the proposed rank code increases with the increase in the number of code words m that describe the given rank configuration of code elements in the feature space. The conducted experimental studies of error variants in the DRP code made it possible to develop a heuristic algorithm for their localization and correction using an auxiliary verification matrix. Testing of the algorithm on a code with a bit rate of n = 6 confirmed that adequacy of the developed algorithm for localization and correction errors of multiplicity 1. Assessment of the correctness of the algorithm operation on codes of a higher bit rate and with errors of a higher multiplicity requires additional research. The authors are grateful to all colleagues and institutions that contributed to the research and made it possible to publish its result. Thank you for your attention.